My name is Sarah Ditke, and this is my presentation on IoT systems for lunar extravehicular activity communications. The first thing to know about communicating on the moon is the lunar propagation environment. We can think of the transmitting antenna as the antenna that's going to be mounted to our lunar lander module, and then the receiving antenna is going to be the antenna that's mounted to, say, an astronaut backpack that's going to be communicating with the lunar lander module. So the transmission antenna has three main factors that are contributing to signal strength. The first being the power transmitted by the antenna, the second being the gain, which is the relationship between the efficiency and the directivity of the output radiation from the input power, and the height of the transmission antenna. And then we have the same sort of thing going for the receiving antenna with the height, the power, and the gain. In between the two, we have path loss, which on the lunar surface can be modeled as 1 over d to the fourth, which is distance, loss. So as the signal is propagating through the environment, it's becoming more and more lossy at a rate of 1 over distance to the fourth power. And then we also have the margin of error in the lunar environment. This can reach up to 20 dB, which is a pretty significant number. So all of these factors either add or subtract from the signal strength between the transmission and the receiving antenna, and we want to have it so that the receiving antenna was able to still add up at the end to dB naught, which is the minimum received signal strength that the antenna can detect the signal from. So limiting factors relating to propagation are the fixed height of the astronaut and the base station. We can't change that. The power transmitted by the Federal Communications Commission, and the limited power and gain of the astronaut suits because of other factors in the astronaut suits, such as converting CO2 back to oxygen, and other biological systems that also require power. So what we can control is the gain of the transmission antenna. So the first way that we can control the focus, the gain of the transmission antenna is by focusing gain along the azimuthal plane. And I found that a good way to do this through my literature review was using a cylindrical Fresnel zone plate antenna. So you have the depiction of the cylindrical Fresnel zone plate antenna here, and what it does is it squashes the beam along the azimuthal plane so it's not losing radiation to space or to the moon. So what we have are two pictures here. The top one is using a typical toroid dipole antenna, with the toroid as the radiation pattern, and then a duplicate one that would be on my astronaut backpack here, and this is the baseline. A typical dipole antenna has about 2.3 dB of gain that's radiating in all directions. And then, like I said before, we have the dipole antenna, but using cylindrical Fresnel zone plate antennas here is a schematic to show you how flattening it along the azimuthal plane would be advantageous to us. So another way of doing this that I found from my literature review would be focusing the transmitting gain along both the azimuthal and the zenal planes into a sort of lobe shape pattern that you see here. And an easy way to do, not easy, but a way to do this is to use a phased array system of antennas with phase shifting to do electrical beam steering. So with phase shifting to conduct electrical beam shifting, we can have this antenna circularly covering the azimuthal plane, but not radiating in all directions at the same time, so that you can focus more directivity towards the one astronaut that you want to communicate with in that moment. So research directions based on these two concepts that I've done. The first is the Fresnel zone plate antenna. Here's a schematic simulation that I did of this antenna at 5.8 gigahertz, which is a Wi-Fi band. So we have the dipole antenna here, and then we have two cylindrical Fresnel zone plate antennas on top, or two cylindrical Fresnel zones on top and on bottom, and this is the radiation pattern that we were able to see from this design, And we can see that along the azimuthal plane, we have a maximum dB of 7.6, which is a much better improvement over 7.3 and contributes to greater range for the astronauts. And then this is the fabrication of this antenna schematic that I did with the plate antennas blocking the destructive radiation signal with copper tape that you can see here. So these are the results that I got from this study. On the left, you see at 5.8 gigahertz, the received signal strength of the receiving antenna from the transmitting antenna, which is just a dipole, is negative 5.55 dB. And then on the right, you see the received signal from the transmitting antenna that does have cylindrical Fresnel zone plates around the dipole is about 3.99 or 4 dB. And so this improvement of around 8 dB is super significant. It's even better than the simulations, which I attribute a little bit to measurement error. But seeing that proof of concept is really helpful for improving astronaut coverage on the lunar surface if you wanted to go the route of using a cylindrical Fresnel zone plate antenna. So another research direction that this can be taken in is using a phased array antenna system with beam steering, and this is something that I started researching in the fall. So the design we have here is 3 series-fed linear pouch antennas fed by Butler matrices on these antenna boards, and 3 of them are positioned in a triangular formation to get 360-degree coverage. And there's an RF switch module and a microcontroller that has a Wi-Fi module on it. The Wi-Fi module is listening for pings from, say, an astronaut suit, and then the microcontroller changes the input of the Butler matrix to tell it to steer in that direction so that it's able to communicate with the astronaut and shift the lobe towards that direction. Continuing on with that design, we have the simulation of the beam steering with this antenna. So this is looking at one board. We have, starting here, we have the lobe going to the left, and then going to left center, and then going to right center, and then going to right when it's fed with each of the different one port at a time to show you that beam steering is successful with this design. And then this is the fabrication of the phased array antenna. So due to COVID-19, I haven't been able to assemble or test the phased array antenna system to see how it performs when it is in an entire system with a microcontroller controlling beam steering, how lossy that can become or how successful that can become due to the school shutdown. So that is future work that I look forward to doing as soon as the school opens back up and I can use the fabrication and the testing equipment that we have. Moving on to my tips for literature searching, I found that the IEEE Explore Digital Library was the most useful for finding my sources. And then for this narrow subject, like surface communications on the lunar surface, I found that citation alerts were not helpful just because this isn't really a hot topic. Not a lot of publications are being done on lunar surface communications. So I didn't find that too helpful. Instead, what I found helpful was using forward and backward searching, as well as looking at searching not only the first but the second and third authors of relevant works to see what else they had worked on in their careers and be able to use those materials which I anticipated to be relevant and most of the time were as further elements in my literature searching. And then in addition to this, I looked at similar subject matter such as extending the range of RFID-based antennas as inspiration for my literature searching works. Some tips I have for using EndNote: compare the citation preview to that citation if you've seen it in papers. That's something I found really helpful. Identify databases that have the best results for exporting and then use those to export papers that you want to use in your database, even if that's not where you found them. And then take notes while preparing to write summaries and do the readings and summaries in one sitting. Thank you for watching my video. I had a great time in ECE 4802 this semester, and I learned a lot about making a research database, constructing a literature review, and writing summaries. So I had a great time. Thank you.